friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. From last few classes, we are discussing about the instruction set of 8051 microcontroller. In that, we already covered data transfer instructions supported by 8051 microcontroller, the arithmetic instructions of 8051 microcontroller. In this class, I am going to discuss about the logical instructions of 8051 microcontroller. So, the most of logical operations performed through accumulator register A. In 8051 microcontroller, most of your logical operations are performed through our primary accumulator register A. That means, if you go to consider different logical operations which are supported by 8051, it will support 7 different logical operations, that is logical AND, logical OR, logical XOR, complement, clear, rotate and then swap. Out of this, the first 3 operations, that is AND, OR, XOR, these are 3 operations what we can call is binary operations. The meaning of this one is, in order to do either logical AND or logical OR or logical XOR, at least we need 2 operands or 2 datas. Out of those 2 datas, one data may be provided by accumulator register. I won't say for 100% always accumulator will provide one of the operand, but maximum cases accumulator must be participating in doing of these logical operations. So, here the meaning of most of logical operations are performed through accumulator itself. So, most of the cases we identify that one of the operand for these logical operations are accumulator register. And after completion of operation, the result also stored in accumulator. I won't say it is 100% was happened for all cases of AND, OR and XOR related instructions, but the maximum cases it was happened. And then coming to the next, by execution of logical instruction, the result conditions are stored in program status word. The meaning of this one is, if you remember the bit format of a program status word PSW, which consists of 4 mathematical flags: carry, parity, auxiliary carry and overflow. These flag conditions are automatically set or reset based on the result what we are getting at the output of A by execution of this logical instruction. That is the meaning of this. These are the 7 different logical operations that are performed by our 8051 microcontroller. To do these 7 different operations, we have the instructions in the instruction set of 8051 microcontroller. And first 3 I can call as binary operations. That means to do these operations, at least we need 2 operands or 2 datas. Coming to the rest of the 4, we can call these are the unary operations. That means to do the operations for these, at least you need only 1 operand or 1 data. That is the meaning of unary operations. Now, we'll go and see what are the instructions that are there in 8051 instruction set to perform these logical operations one by one. See here, friends. So, the first one is ANL, means AND logical. ANL means AND logical. This is the instruction which is used to perform bitwise logical AND between the operands. I repeat, this is the ANL instruction is used to perform logical AND between bitwise the both input operands. So, if I take example here, ANL A comma hash 25H. The meaning of this one is, the immediate value 25H is logical AND with the content of accumulator. Let you can assume, friends, before execution of this instruction, A value is equal to some 89H. A value is equal to 89H. What is its equivalent binary? 1000 and 1001. That is the binary equivalent of 89H. This A value is now logical AND with immediate value has 25H. So your second operand is 25H. What is its equivalent binary? 00 10 01 0. Now our controller can do logical and bit by bit between 89H and 25H. So 1 is ending with 1, 1, 0, 0, 0, 0, 0, 0 and 0. Now my final result here is 0, 1H. After execution of this logical AND between a content of A with immediate value 25H, my result is 0, 1H. Again it will goes to the destination operand, that was accumulator register A. I hope you understand the example of this ANL space A comma hash 25H. Before I was shift to the second one, I would like to add one more point here, that is the operands for this ANL instruction is our CPU registers, or it may be one of the CPU register and another one is a content of memory location, or it may be a memory location content and an immediate value, or it may be a CPU register and immediate value. That means there are 4 different possible operand combinations are used in ANL instruction. I repeat, the operands for this is number 1, both may be registers. Both may be registers. And second thing is, one is a register and second one is the memory location content. And my third one is a register and immediate value. Register and immediate value. This is here our example belongs to this third category. And coming to the fourth one is nothing but memory location and immediate value. So these are 4 different varieties of operands you may identify in the operand fields of an instruction ANL. ANL means unlogical, bit by bit between the operands. So that is the meaning of this particular instruction. And next coming to my second instruction is that is ORL. ORL means or logical. ORL means or logical. Here also the conditions what we know for ANL instruction, the same conditions also applied for ORL instruction. Only the difference is by using ANL we do bit by bit logical and between the operands, but by using ORL we do logical or bit by bit between the operands. And apart from that, everything is same as ANL instruction. That means the different possible combinations we identified in the ORL instruction operand field was both may be registers, that is one possible combination. The second possible combination is it may be a register and a memory location, and third possible combination is a register and immediate value, and fourth possible combination is a memory location and immediate value. These are the 4 possible operand combinations we identified in operand fields of ORL instruction. Again, for better understanding, I took an example here, that is before execution of an instruction ORL A comma or not, my A value is equal to some 75H and register or not value is some 18H. 18H. So A value is a 75H and or not value is 18H. What is the equivalent binary values? 75H equivalent is 0 111, that is equivalent to 7, and 5 0 1 0. So we know that guys, the representation. This is an hexadecimal number, so that if you write in a binary, for each and every hexadecimal we are representing with 4 binary bits. That we know that. That's why I was getting this type of notation. This is the binary equivalent for hexadecimal number 75H. Now similarly, the binary equivalent for 18H, that is 0001 and 1000. This is 18H. Now do logical OR bit by bit between A value and register or not value. We know that for a logical OR, both inputs are 1, the output is 1, or at least one input is 1, output is 1. If both inputs are 0, then and only output is equal to 0. You know this. This is from our digital circuits. Right. So here 1 0 case, here at least I have only 1 1. So output is 1. Here both inputs are 0. So output becomes 0. Again 1, 1, and both inputs are 1, then 1, 1, 1, and then 0. Now what is its equivalent value? It is a 7DH. So after execution of instruction ORL stays A comma or not, the result is a 7DH. This 7DH finally stored in register A because register A is placed at destination operand field. And one more thing you have to remember, friends, after execution of this instruction ORL A comma or not, we are getting this result. Along with that, we may get some result conditions. Those are automatically stored in PSW. That you remember. And next coming to my next instruction is that is XRL. That means XRL means XOR logical. XOR logical. So XOR logical between the operands. So it is also comes under our binary operation like our previous two. That is logical OR and logical AND. But the conditions what we observing in case of logical AND and logical OR case, the same things are applied for logical XOR also. But only the difference is in case of a logical XOR related instruction execution, we do logical XORing between the operands. Apart from that, everything is same as our previous cases. That means the operand combinations what we identified in the instruction that was same. That means again for XOR related instruction, that is XOR will have both operands may be registers, or one more combination is a register and a memory location, or one more combination is a register and immediate value, or one more combination is a memory location and immediate value. These are the four different possible combinations we use for this XOR related instruction also. Right. For again better understanding, I'll go for an example, that is XORL space A comma 60H. Once you see this instruction, we can easily identify that our instruction is in direct addressing mode, because here our source operand is address is source operand is here 60H as well as A, and here the 60H is nothing but an address of our data, address of data. So that we know that. So here address of data is directly placed in the instruction itself, so that our instruction is comes under direct addressing mode. So before execution of that, the content of accumulator is some ABH. The content of accumulator is ABH, and the content of 60H. The content of 60H. See here, friends, I am not using direct. I am not writing directly 60H. I am writing 60H with the base. That means here I was considering the content of 60H. That means here this 60H is treated as address of data. It is not data directly itself. So the content of 60H is, I was assuming, some EFH. So what is their binary equivalence? For AB is 1010, that is A, 1011, that was B. So ABH equivalent is 1010, 1011. And coming to FEH, it is for EFH, that was at 1110, and then 4 ones. Now do logical XOR between these. What is the condition of logical XOR? If inputs are same, output is 0. If inputs are differ, output is equal to 1. You know this. Again, it is I was considering from our digital circuits. You remember that. So for first two bits, my inputs are same, output is equal to 0. For next case, the inputs are differ, output is 1. Again, inputs are same, 0. Again, inputs are same, 0. Inputs are same, 0. And inputs are differ, so 1. Again, 0. Now my result here is 44H. So 0100, 4, 0100 again 4. So result is 44H. So after execution of XRL A comma 60H, my result was 44H. Again it is goes to accumulator itself. So that is the meaning of XRL A comma 60H instruction. And next coming to my next instruction was CPL. CPL means complement. CPL means a complement. That means I can complement the content of an operand. So here I consider an example CPL space A means complement accumulator value. One thing you remember, friends, here this complement is one's complement. Here this complement is, you remember, which is one's complement. You remember that first thing. So once we are considering one's complement, what happens? The operand content which may be changing from 1 to 0 and 0 to 1. If I consider an example CPL A, so before execution of that, my A value is some 98H. A value is some 98H. What is its equivalent binary? 9 is 1001, 8 is 1000. So this is equivalent for 98H. So this is the scenario that I was found in accumulator register A before execution of an instruction CPL A. CPL means complement A. After execution of that, what happens is, one's complement we know that interchanging of 1 with a 0 or 0 with 1. So it is changes to 1, 1, 1, 0, 0, 1, 1, 0. Now what's the result now? It is equivalent to 67H. It is 67H because 0110 equivalent to 6 and 0111 is equal to 7. 67H. Now this 67H again goes to accumulator itself. This is the result what I found after execution of CPL space A, and before execution of that CPL A, my A value is 98H. I hope you understand this. And next coming to another instruction is CLR. CLR means clear. CLR means clear. So here my example is CLR A means clear accumulator content. Clear accumulator content. That means by execution of CLR space A, what happens is, what all the data that was exist in accumulator, it will be changes to 0. It will be changes to 0. So see here friends, before execution of this instruction, our A value is equal to some 23H. Let you mention that 23H. What is the equivalent binary? 0010, 0011. This is a 23H equivalent binary. And after execution of this CLRA, this accumulator content, what happens is, it was clear. That means this result is equivalent to 00H. So after execution of that CLRA, my accumulator value was clear. That means accumulator is loaded with 00H. That is the meaning of this. And next coming to my next instruction is, that was RL. So from next 4 instructions, that is RL, RLC and RR, RRC. These are 4 instructions we can call as rotate related instructions. Rotate related instructions. So these rotate related instructions, we always do the content of accumulator. We always do this rotate right operation only on the content of accumulator. That is number 1. And number 2 here is, in case of these rotate related instructions, we can rotate the content of accumulator only by 1 bit position, either to right side or to left side, either right side through carry or left side through carry. That you have to remember. Now, I start with my first instruction, that was RL. RL means rotate left without carry. So, here my example is RL space A. That means rotate left the content of accumulator. For better understanding, I can go for an example. So let you can assume friends, this is my accumulator is. We know that accumulator is an 8-bit register. So this is my accumulator, has an 8 bits like this. So bit 0, to bit 7. And this bit 0 we consider as LSB, and this one we consider as MSB. So in rotate left, the bits are moving from LSB side to MSB side. Beside of MSB, we may found a carry flag. We may found a carry flag because RL means rotate left without carry. So before execution of my RL space A value is equal to, I was assuming some ADH. What's the equivalent value in binary? A is nothing but 1010, D is nothing but 1101. At the same time, my carry flag CL value initially 0. Initially, carry flag value was 0. This is the scenario before execution of an instruction RL space A. Now, after execution of RL space A, what happens? Now the bits are moving from LSB side to MSB side. So in that case, this MSB bit goes to carry as well as the same MSB bit goes to LSB also. I repeat, in the execution of RL space A, the bits of accumulator was moving from LSB side to MSB side. In that process, MSB bit goes to carry as well as it will goes to LSB. Initially carry value was 0. Now what happens? This one is moved to here, the same one also moved to here, this one shifted to here, 0 shifted to here, 1 and 1, 0, 1 and then 0. Now what's the scenario of this A and CY after execution of RL space A? After execution of RL space A, my A value is 0101, that is 5, 1011, that was B. So accumulator value is 5BH. Then what is the carry flag value? Carry flag value is equivalent to 1. So this is the values that are present after execution of an instruction RL space A. If I consider A value is this and carry value was this. I hope you understand, friends, what this is, RL instruction is. And next, coming to my next instruction is RLC, means rotate left through carry. Rotate left through carry. It is similar to previous one, but only one difference is, in previous case the carry flag was not involving in rotation operation, but now in this instruction execution, carry flag also participating in rotation operation. So see here, friends, what happens. Again our structure is like this only. Again I was assuming accumulator value is ADH, carry value was 0 before execution of my instruction RLC space A. Again it is a rotate left through carry, so that accumulator bits are moving from LSB side to MSB side, and only one difference here is that is MSB bit goes to carry, at the same time this carry bit goes to LSB. So now this is not 1, now it is 0, because previously our carry value was 0. So see here, friends, this is the scenario of our accumulator before execution of an instruction RLC space A. A value is ADH. So A means 1010, D means 1110. Initially my carry flag value was 0. After execution of this instruction, what happens? Carry bit goes to LSB and the bits of accumulator was moving from LSB side to MSB side. In that process, MSB bit goes to carry. So that here it is 1 and now this is shifted to here like this. What a final value? Here is accumulator values. Again it is 0101 is fine. 1010 is now A. So accumulator value is 5AH and carry value is still 1. So only the difference between this and previous instruction is, in previous instruction execution our carry flag was not participating in the rotation operation, but now in this case the carry flag also participating in a rotation operation. So I hope you understand the structures, right? The difference between RL as well as RLC. And next coming to the next instruction is RR. RR means rotate right, again without carry. Rotate right without carry. So again here it is similar to our RL instruction, but the difference is RL is rotate left, but RR is rotate right. That you have to remember, friends. Now, if I go for an example, RR space A. Again, if I consider example, before execution of this, my A value is some 23H and carry flag value is initially 0. A value is a 23H and carry flag value is initially 0. Now, this is my accumulator again. We know that accumulator is an 8-bit register. So the bits of accumulator is organized like this. So initially it is loaded with 23H. So 23 means 0010, 0011. And initially your carry flag was 0. So this is my LSB and this is MSB. In rotate right, the bits of accumulator was moving from MSB side to LSB side. So that beside of LSB, you may have a carry flag CY. Initially that was loaded with 0. So now in execution of RRA, rotate right accumulator value, that means the bits of accumulator was moving from MSB to LSB. In that process, LSB bit goes to carry as well as this LSB bit also goes to MSB position. So then what's the change that we identified in our bits of accumulator as well as carry? So LSB bit goes to carry, so that carry value is 1. Now the same LSB was moving here and this bit shifted to here, 0, 1, 0, 0, 0 and then 1. Now what is the equivalent value after execution of RR instruction? What A value? A value is 1001, that was 9, 0001, that is 1. So 91H, that was accumulator value, and my carry value was 1. So this is the result what I was found in both accumulator and carry after execution of my instruction RR space A, that is rotate right accumulator content without involving of carry. So this is about this RR instruction. Next coming to the next instruction is RRC, means rotate right through carry. Only the difference between this and previous one is, in previous case the carry flag was not participating in a rotation, but now the carry flag also participating in a rotation operation. So here also my example is RRC space A, means rotate right through carry the content of accumulator. So for better understanding, I can give a diagrammatic form of this instruction execution. Again you can assume, friends, this is my accumulator register A, accumulator A. So the bits of accumulator is like this. This was LSB and this was MSB. In rotate right, always the bits are moving from MSB side to LSB side. So beside of LSB, we have a carry flag CY. If your instruction is rotate right through carry, LSB bit goes to carry as well as now the carry bit goes to MSB. Like this. Again bits are moving in this direction. So that's it. And coming to my last instruction is a swap. Last instruction is to swap. So this swap example is swap A, that means exchanging of a lower nibble with upper nibble of accumulator. I repeat, swap A means exchange the nibbles of accumulator itself. That means lower nibble of accumulator becomes upper nibble and upper nibble of accumulator becomes lower nibble. For better understanding, I take an example. Before execution of swap A, accumulator value is some 92H. Let you consider. So in this case, 9 is considered as upper nibble and 2 is considered as lower nibble. LN means lower nibble, UN means upper nibble. After execution of swap, these nibbles are exchanges. That means after execution of that, your accumulator value becomes 29H. That means lower nibble shifted to upper nibble and upper nibble shifted to lower nibble. So after execution of swap A, this 2 becomes upper nibble and this 9 becomes lower nibble. Only the nibble's position was exchanged in accumulator. So that was happened by execution of an instruction swap. So these are the different logical instructions which we found in 8051 instruction set under logical instructions group. I hope you understand these instructions. So in the next class, I am going to discuss about another group of instructions which are there in our 8051 microcontroller. Thank you for patiently listening.